now we're going to see the total random translational kinetic energy for the collision on the ideal gas and the root mean square velocity. So in the previous video we saw the pressure, force and momentum in these ideal gas collisions. So quickly as a reminder, here we have the particle that is pumping here and comes back here. So we saw that the momentum for a particle, the change in momentum for a particle was 2 times the mass times the change in velocity in the x component, absolute value. We also saw that in order to occur collisions on an interval dt, we need that the particles be at a distance of dt times the velocity. And so we have a cylinder that has this width dt times the absolute magnitude of the velocity, and here we have the area of the cylinder, let's say A. So we have that the volume is A times the absolute value of the velocity times dt. Now we are supposing that the number of molecules per volume, so in the cylinder, is constant. So now we have n is equal to n over v times v. Here we have that the area times the velocity times dt over the volume times the number of molecules is equal to the, here will be the number of molecules, and half of them are going to the wall, half are going away, so half of the molecules will collide. So 1/2 of the area times the velocity times the time times the number of molecules divided by the volume. Then we saw that the change in momentum over the change in momentum was this multiplied by the change in momentum for the particle. So this is just how many momenta are we going to have. So times 2 times the mass times the absolute value of the velocity. So here we have the area times the square of the velocity in x, the number of molecules dt over the volume. Now the was the momentum, the change in momentum. Now the change in momentum over change in time is we divide everything by dt. And lastly, this is force. So force divided by area is pressure. So we have pressure is equal to the velocity square times the number of molecules divided by the volume, and here I forgot to put the mass. Alright, so now remember the equation for the ideal gases, that the pressure times the volume is equal to the number of moles times the universal constant of gases times the temperature. So here we will substitute the pressure here. So we have the velocity in the x component square times the number of molecules times the mass is equal to nRT. So we have the velocity is equal to, or the magnitude of the velocity is equal to the square root of the velocity in x squared plus the square of the velocity in y plus the square of the velocity in z. We square both sides, and we see that the velocity on the x, y and z component is practically the same. So we can say that the average velocity square is approximately the 3 times the square of the velocity in x. So the velocity in x is approximately 1/3 of the average velocity square. So we will substitute this here. So we have 1/3 of the square velocity, average square velocity, times the mass times the number of particles is equal to nRT. So if here we could have 1/2 of the mass times the velocity square, we would have kinetic energy. So we can multiply everything by 2, divide everything by 2. So we have 2/3 of the number of molecules times the kinetic energy is equal to nRT. So we have n times the kinetic energy, N times the kinetic energy is equal to nRT divided by times 3 halves. So this is called the total random translational kinetic energy. So this is called kinetic energy sub TR. This is to remind us that this sub TR is to remind us that the kinetic energy for vibration or rotational energies could be different, and we could have some other energies there, but not for translational energy. So here we have this is equal to 3 halves nRT. So this is our first equation. Next is if we want to know the translational kinetic energy of one molecule of gas, then we will divide this by the number of molecules. So this will be equal to 3 halves of nRT divided by the number of molecules. Now, remember that the number of molecules is equal to the number of moles times the number of Avogadro. Then n, the number of moles, is equal to n divided by Avogadro's number. So here we have kinetic energy of the translational kinetic energy of one molecule is equal to 3 halves of number of molecules divided by Avogadro's number times RT divided by number of molecules. We kill this and we have that the kinetic translational kinetic energy of one molecule, this is the translational kinetic energy of one molecule, is equal to 3 halves of RT over Avogadro's number, and the universal constant of gases over the Avogadro's number is the Boltzmann constant. So we have translational kinetic energy of one molecule is equal to 3 halves of Boltzmann constant times the temperature, and this will be equal to the kinetic energy is just 1 half of the mass times the average velocity square. So this is the second equation. Now if we want to put this written in other way, is we will substitute this by this, and R can be substituted by, or let's put it like this. So we'll have that pressure times volume is equal to the number of molecules divided by Avogadro's number times R. Remember, we saw that R over Avogadro's number is the same as Boltzmann constant. So here we can put it as Boltzmann constant times the Avogadro's number times the temperature. So we have pressure volume is equal to the number of molecules times Boltzmann constant times the temperature. So this is other equation. And now look, here we are talking about the translational kinetic energy of one molecule. If we want the translational kinetic energy per mole, that is, we are not talking per one molecule, we are not talking about one molecule, we are talking about 1 mole. In 1 mole we have 6 times 10 to the 23 molecules. So we have Avogadro's number. So we will multiply this by how many molecules are on 1 mole. In this case, we will multiply it times Avogadro's number. So we have now that Avogadro's number times the translational kinetic energy, or well, this will would be the translational kinetic energy, per mole. So this would be equal to here is 3/2 of Boltzmann constant times the temperature times Avogadro's number. So remember that Boltzmann constant is R over Avogadro's number. So here we just have 3/2 of the universal constant of the gases times the temperature. So this is our equation. Now, lastly, for the velocity, Alright, now we have kinetic energy here equals to 1/2 mass times the square of the velocity. So we have the average velocity square is equal to 3 Boltzmann constant times the temperature. Alright, so divided by the mass. So we have that the average velocity is the square root of 3 times Boltzmann constant times temperature divided by mass. But remember that Boltzmann constant is universal gas, the constant of universal gases divided by Avogadro's number. So this times temperature divided by the mass. So we have the average velocity is also equal to the square root of 3 times the universal gas constant times the temperature divided by this is the molar mass. So this is the weight of just one molecule in Daltons. This is the Avogadro's number. So when we multiply this, we have the mass of a mole of this gas. So capital M. So we have that the average velocity is either the square root of 3 times the universal gas constant times the temperature divided by the molar mass, or the average velocity is equal to the square root of 3 times Boltzmann constant times the temperature divided by the mass of just one molecule. So now we have these formulas are the formula for the total random translational kinetic energy is 3/2 of nRT. So this would be what is the total random translational kinetic energy for a mole of whatever gas it be at 27 degrees Celsius. Then this will be the total kinetic energy times, and this will be 3/2 of 1 mole times the universal gas constant, whatever it be, times the temperature. 27 degrees Celsius is the same as 300 Kelvin. The other is what is the translational kinetic energy per molecule at 27 degrees Celsius. So here we have it, 3/2 times Boltzmann constant at that temperature. What is the total the translational kinetic energy per mole of this gas at 27 degrees Celsius? Then we would have 3/2 of R times T. And lastly, what is the average velocity? Let's say now here we need the mass of methanol at the same temperature. So it will be the square root of 3 times R, whatever it be. The temperature is 300 Kelvin. Divided by the mass. This is the molar mass. So the mass of methanol is one carbon, is carbon, OH, and 3 hydrogens. So the mass is 4 hydrogens. 1 oxygen is 16 in mass, 16 Daltons. Carbon is 12, so we have 16 and 16 is 32. 32 Daltons in 1 mole we have 32 grams. So here divided by 32 grams, and we will convert this to 32 kilograms in order to achieve here with all the units meters per second.